Hello, Hustle. 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 What do you do, Hustle? Hello. Hello, Hustle. Come here. Come here, Hustle. Hustle. Come here. Hustle. Thank you, Hustle. What to do? What to do? What to do? Hmm? What to do? What to do? Oh, you want to go? All right. I am going to go ahead and get started. I know the number of concurrent viewers is very low, but I'm just going to do it because class has begun. Okay. This camera got a little bit messed up. I'm glad you love where your grade is at right now. So, as I mentioned a little bit, maybe a couple weeks ago, I recently learned that they have removed some topics from the AP Physics 1 exam this year. And those topics that they removed were Ivan. Hang on a second. Ivan, don't do that. You can't hit Hazel. Ivan. You can't do that. The cat was hitting the old dog, the old granny dog. As I was saying, the waves and circuits were removed from the AP Physics 1 exam. And so I learned about that when we were like partway through waves. And so what I decided to do was just do a sort of an intro to circuits, and then we'll circle around and study it again after the AP exam. So what I'm going to be doing now is sort of reviewing while simultaneously talking about a really important subject or a really important thing that appears on the AP Physics 1 exam, which is experiments, okay? And so obviously we haven't had the chance to do experiments since we've been distance learning, but we're going back, and so my plan is when we're back in person to do experiments for the in-class portion and then do review for the out-of-class portion. So that's what we're going to do. And so one of the things that you might be asked to do on the AP Physics 1 exam is, number one, design an experiment. Or number two, you might be given experimental data and asked how would you interpret that data, okay? So what we're going to start talking about is experimental physics. Okay, and so basically what I'm going to do is I'm going to be just talking about some common experiments you might see on the exam, and we're going to review in that way. So today we're kind of going to be mostly talking about kinematics experiments. So I want to remind you that there were three equations that were used in kinematics very frequently, and they were delta x equals v naught t plus 1/2 at squared, v final equals v initial plus at, and v final squared equals v initial squared plus 2a delta x. And these equations, of course, assume that the acceleration is constant. So if you don't have a constant acceleration, you can't use these equations. This equation, the first one, is probably the most important. Okay, and the reason is that when you are doing a kinematics experiment, the data that you collect, so let me talk about like a simple kinematics experiment. You might just have a ramp, okay? And you have a ball that is going down the ramp. So what you might do is you might use a meter stick to mark the ramp, okay? And then you use a stopwatch to record the time at which each of these markings is crossed, okay? And so what you would get, you get the following data. So you would get a data table of position, so how far has the ball traveled at a certain time. Okay, so maybe these are 50 centimeters apart or something, so you have the displacements are 0.5, 1, 1.5, okay, and then 2, and then maybe the times are 1 second, 1.4 seconds, ... Okay, so you get, when you are doing a kinematics experiment, the data you are collecting is position and time. Okay, and so notice how this is the kinematics equation that has position and time. This one has velocity and time. This one has velocity and displacement. So this is the experiment that basically, or this is the equation, excuse me, that matches up with the data that we actually collect. Okay. We could get velocity versus time, but that is less common because in order to truly measure the velocity, you need something like a radar gun, right? If you think about police officers handing out tickets, they have a radar gun. So that is not measuring position as a function of time. It's measuring speed using the Doppler effect, okay? So that's directly measuring the speed. But when we're just doing a simple experiment, in physics class, we don't have that kind of technology to directly measure the speed. So what we actually measure is position versus time, and we can use that to deduce the speed or to deduce the acceleration. All right. So in particular, there are two common variants of this equation. So I will talk about those. So one is what if the object has a constant velocity? Okay. If the object has a constant velocity, then that's another way of saying that the acceleration is equal to 0. And so in this kinematics equation, if the acceleration is 0, that is going to kill the second term in this equation. Okay, so the equation will become delta x equals v naught times time. Okay, so that's a special case of this equation. Another common situation is that it's accelerating, but it starts from rest. Okay, so it starts at rest, and so that means that v initial is 0. And so if v initial is 0, that's going to kill this first term in the equation. And so we would get delta x equals 1/2 at squared. All right. So what if you did this experiment? So this experiment is obviously the ball is going to accelerate down the ramp. Okay, and so we want to know in this experiment, what is the acceleration? So let me write this here. So the objective of the experiment is to measure the acceleration. All right. And we can't directly measure it. What we get is position versus time, and we have to use that to deduce what the acceleration is. Okay. So what we want to do is we want to learn how to deduce the acceleration from position and time data. All right, so that's what we're trying to do here. So one option that you could use to do that is so let's say that this is the actual data. You could take a single point. All right, take a single point. So for example, we have time is 1, delta x is 0.5. So we could plug that into this equation. We could say, okay, delta x equals 1/2 at squared. All right. And then the time is 1, so I have 1 squared a equals 0.5 1/2 at squared. And then I could solve this equation. I get that the acceleration is 1 meter per second squared. And then I could take the second data point. So this option is taking a single point at a time. So now I have that the time is 1.4. So I have 1.4 squared equals 1/2 a, and then it has traveled 1 meter. And again, this gives you something where a is approximately 1 meter per second squared. Okay. And so maybe you take all these and you average them and you get the average acceleration. But this is not a good method, okay? So I'm going to actually cross this out. You do not want to take a single point at a time. Why is this flawed? It's because this method only uses one data point at a time. Okay? So if you just take a single position and a single time and you use that to deduce the acceleration, then you take another one, you're only using one data point at a time. Okay? And the individual data points are susceptible to random experimental noise. Okay? Okay, so for example, you might be using a timer, and your ability to time it, you have a flawed. You're a human being. You have a certain reaction time. Sometimes you might click the timer too early. Sometimes you might click it too late. And so individual data points are subject to experimental error. Okay, but if we use all of the data points collectively, then the experimental error tends to cancel out. Okay, so this is a case where using all the data points is greater than the sum of the individual points. Okay, it's like the whole is greater than the sum of the parts. Okay, so here's what we want to do. Here's the correct way to process data such as this. Okay, what we would do is we would graph displacement on the vertical axis. And if we did time on the horizontal axis, we can see that the relationship is delta x equals 1/2 at squared. Okay, and so this data is going to kind of look like, so this is a parabola, right? It's t squared. So the data is going to kind of look like this. All right, and then you have a line of best fit that goes like this. And so notice how a line of best fit uses all of the data points collectively. And so for that reason, it is much less susceptible to experimental error. Okay? So that is why we want to always graph the data and do the line of best fit that's using all the points collectively. But this is a problem. Okay? Because this relationship isn't linear. So this is not a line. Okay? So that makes it hard to analyze. Okay? Lines are easy. Lines have two very simple ways to describe them. They have slope and they have intercept. Okay? Lines are simple. So what we want to do is we want to actually linearize. So you must linearize the graph. Okay, so that means change the variables that are on the axes. So we are going to choose an x, if you will, so a horizontal axis variable, and a y. So the relationship is y equals mx. Okay? So we're not going to put time on the horizontal axis. Okay, so let me show you how that works. So I know that my relationship between the variables is going to be delta x equals 1/2 at squared. All right, but what if I didn't put time on the horizontal axis? What if I put time squared on the horizontal axis? Okay. So I have, what if I had a graph of displacement versus time squared? All right. So then it's not time that's acting like x, it's time squared that's acting like x. And then delta x is on the vertical axis, so delta x is kind of acting like y. And then, as we know, the number that multiplies x is the slope. Okay, so we can see that 1/2 a is multiplying x, so that must be the slope. So this graph, if I graphed displacement versus time, I get a bendy curve of best fit. I get a curve. But if I graph time squared, my data points would look like a straight line. So we have linearized the data. We have chosen our variables so that the relationship between them is now linear. Okay? And so then you would get a line, you do the line of best fit, and the slope of that corresponds to the acceleration divided by 2. Okay? So what if the slope was 5? Then I would say, well, a over 2 equals 5, so then the acceleration must be 10. All right? So how do we get, what does that mean to graph delta x versus t squared? Well, if you had, all right, so if you have a, I'm just going to make up a data table. So what if you had, 1 and 1, 2 and, I don't know, 3, 3 and 7, 4 and 10. So if you made a data table of delta x versus t squared, you're keeping all of the delta x's the same. So 1, 3, 7, 10. But the corresponding times you're going to square. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So these are the ordered pairs that you are graphing. So notice how the ordered pairs are different. If you were to graph position versus time, these would be your ordered pairs. And if you're graphing position versus time squared, you are now graphing some different points. Okay? So that's what I mean by that. So that is called linearizing the graph. So what if I had a ball that was rolling across a flat surface? So I could do the same experiment where we have a ball that's rolling across a flat surface. Okay. And so again, I mark out points along the ground and I record the time at which the ball crosses each point. Okay. And so I get a data table of position versus of displacement versus time, just like before. But now acceleration is equal to 0 because it's just a flat surface. Okay, here it was a ramp. And so I knew it was going to be accelerating here. But now it's a flat surface, so I know that it's just going to roll at a constant velocity, neglecting friction. Okay? So in that case, the equation that this data is going to obey is now delta x equals v naught times time. All right? So in this case, the graph is already, or the data is already linear. If I put delta x on the vertical axis and time, not time squared, but just time on the horizontal axis, then delta x is acting like y, time is acting like x, and then the number that multiplies x is acting like slope. So this is already the equation of a line, and the slope is the velocity of the ball. Okay, so if the data is already a graph or already a straight line, then we don't need to change variables to linearize it. All right, so it depends on. So basically, the lesson is that in order to linearize, okay, you must know the theoretical relationship between the variables. Okay, you must know the theoretical relationship between the variables in order to linearize a graph. So let me give you an example of this. And this example is going to review a little bit of energy. So this is an energy experiment. All right. So suppose, again, I have a ramp, and then I have a flat part. All right. And so I have a ball, and what I do is I measure the height of the ball above the table. And then once the ball gets to the bottom of the table, I record its speed. Okay, so I have height, initial height, and speed. And then I do the experiment again, only this time I release it from a different height. So maybe that's y2. And then I get a different speed at the bottom. Obviously, it's going to be a greater speed at the bottom. And then I release it from higher up still. And I get a different speed at the bottom. Okay. And so I develop a data table of initial height of the ball and speed at the bottom of the ramp. Okay. So now, how are these variables related to theoretically to each other? Okay. Theoretically, if I wanted to solve for the speed at the bottom of the ramp, I would use conservation of energy. Okay, so I have initial energy equals final energy, and then the initial energy is gravitational potential. So I have mgy, and then the final energy is kinetic. So I have 1/2 mv squared. So then I notice that the mass cancels out, and then I multiply both sides by 2, And what I get is v squared equals 2gy. All right? So what if I decided to graph just speed versus y? Speed at the bottom versus y. Okay? According to this equation, the theoretical relationship between these variables is not linear because of the presence of this v squared. Okay? It would have to be v equals a constant times y in order for this to be a straight line, but instead it's v squared is a constant times y. Okay? So this graph is not a straight line. Okay? But how could I linearize it? Well, what if instead I put v squared on the vertical axis and y on the horizontal axis? So then v squared is acting like y, right? Because the vertical axis variable is usually called y in math class. And then y is acting like x. And so if I make those replacements, the number that multiplies x is the slope. And so I can see that the slope is going to be 2g. Okay? Which would mean it should be approximately 20 meters per second squared. So, so what we've done here is we have linearized the graph. Now, what would happen if your data looks like this? So that it's obviously not a straight line. So this is the theoretical relationship. And what if this is the actual collected data? All right. Basically, this relationship is your hypothesis, if you will. And so you graph the data according to your hypothesis for how the variables should be related to each other. And if you don't get a straight line, then that means the hypothesis is wrong. So if your actual data looks like this, where it's all curvy, that would say that your data suggests that the conservation of energy is not true. Okay? Now, of course, many physicists have done experiments on conservation of energy, and it most definitely is true. So probably what that would mean is that there's something in the experiment that you're not understanding. There's some effect that you're not accounting for in your hypothesis. Okay? So maybe friction or something like that. Or the fact that the ball is rolling, not sliding. So we needed to worry about rotational kinetic energy. Something like that. So there's something. So if you develop a theoretical relationship and you linearize that relationship, and then you find that it is not aligned once you actually graph your data, then that means that your theoretical hypothesis is wrong, okay? Or that something else is going on in your experiment. Okay, so so basically what I'm saying is that if conservation of energy is true, a graph of v squared versus y should be linear. And the slope should be 2g, which is approximately 20 meters per second squared, if this was on Earth. Okay? So since I'm talking about kinematics, I also wanted to just really briefly review projectile motion. Because today's quiz has a little bit of projectile motion on it. So kind of what we do when we're reviewing for the AP exam is we're just jumping around to a bunch of different physics topics. So what you want to focus on, in the normal flow of the class, we might be studying projectile motion, and so you might have projectile motion down in your mind. You can do projectile motion problems. But then we move on to rotational dynamics, and then you forget about projectile motion and you are really good at rotational dynamics. So the AP exam has everything. So we want to kind of increase your flexibility, your ability to jump between different areas of physics rapidly. Okay, so we're jumping between kinematics equations, then we're jumping to conservation of energy, then we're jumping to projectile motion. Okay, so we're trying to improve your ability to jump around quickly between areas of physics and not just have one area of physics at a time in your mind. So the equations of projectile motion, there were two of them. One was delta y equals v y naught t minus 1/2 gt squared. So what that meant was there's a t squared term for the delta y, so that means the vertical motion is accelerated. Okay? And then delta x, the horizontal motion is not accelerated, so there's no t squared term in the delta x equation. So what do these mean, delta y, or vy naught and vx naught? Well, when you throw the projectile or launch it, it has a certain launch speed, and then it has a certain launch angle. Okay, and so what we can do is we can make a velocity triangle, and the vertical component of that is the y component of the initial velocity, and the x component is the x component of the initial velocity. So we would use trigonometry. So this is opposite the angle, so that would be v naught sine of theta. This would be v naught cosine of theta. Okay? And so there were two main problems that we discussed in projectile motion. One of them is angled launch across a level surface. And so in that type of a problem, you've got a level surface. So here's the ground. You launch a projectile. It has a certain launch speed and a certain launch angle. Again, you're going to use that launch speed and launch angle to get vy naught and vx naught. Okay, so then it goes, and maybe we want to figure out how far it goes or something like that. All right, so the important point about this is that the projectile starts at a certain elevation and it ends at the same elevation. So you have delta y equals 0 in this problem. So then when we plug that into your kinematics equation, you get, instead of delta y equals that, you get 0 equals vy naught t minus 1/2 gt squared. And then you get the delta x equation is unchanged. Okay, so in other words, having more knowledge, these are the general equations of projectile motion, but having more knowledge allows us to refine those equations to a particular scenario that we're studying. Okay, We could also have horizontal launch off a cliff. Horizontal launch off a cliff. So that looks like this. So the cliff has a height h. So if it's a horizontal launch, then that means that the initial y velocity is 0 because you're throwing it horizontally. You're not throwing it up at an angle or down at an angle. You're throwing it perfectly horizontal. If you're throwing it up at an angle, then Vy naught would be positive. If you're throwing it down at an angle, Vy naught would be negative. Okay? Important point. This is the initial y velocity. Okay? Once you let go of it, gravity is going to curve it downward. And so as time goes on, Vy naught will become negative. All right? If Vy naught remained 0, it would just continue to go out in a straight line indefinitely. Okay? The other thing is that it drops a height h, a distance h before hitting the ground. So we have delta y is negative h. All right? So again, these are the general equations, but we can use the specific situation to refine that equation and simplify it. So delta y is negative h. Vy naught is 0, so we just have negative h equals negative 1/2 gt squared. And then the delta x equation is unchanged. Okay? So that's how that works. All right, so that's my lesson for today. We've reviewed kinematics and we've started discussing some techniques in experimental physics. So I will see you in the Zoomer.